Well, Jess, a mesmerizing scene is taking place in the North Bay. For the first time in 6 years, the round spillway at Lake Beressa is active once again.
A rare sight has returned to California's Lake Beressa for the first time since 2019.
The mystery began with an unusual sonar reading during a routine environmental survey in the southern basin of Lake Michigan. Scientists from a joint research team comprising members of regional universities and federal agencies were monitoring lakebed conditions, primarily looking for geological activity and sedimentary shifts. What they found instead were deep, perfectly round holes scattered across a specific stretch of the lake floor, dozens of them, each measuring several feet in diameter and plunging deep into the otherwise uniform silt. The sonar images were crisp and unmistakable. The holes were spaced at irregular intervals, but all shared nearly identical proportions. For seasoned researchers who had mapped much of the Great Lakes floor in exhaustive detail, this was something new and inexplicable. Before we start, smash the like and subscribe buttons for more updates. Curiosity turned quickly into urgent inquiry. Researchers deployed underwater remote-operated vehicles, ROVs, to capture visual confirmation. As the cameras descended into the cold, shadowy depths, the team was struck by the precision of the formations. The holes appeared as if carved with mechanical accuracy, their edges clean and sharply defined. Unlike natural sinkholes, which often result from the collapse of porous bedrock or underwater erosion, these features lacked the telltale signs of gradual formation. There were no collapsing walls, no sediment trails, and no surrounding instability in the terrain. It was as if something had punched through the lakebed from above, or emerged from below. Initial measurements recorded some of the holes descending over 10 feet, with a few probing even deeper. More peculiar still was the absence of displaced material. Where had the sediment gone? If this had been a matter of falling debris or collapsing crust, there should have been mounds nearby or visible sediment clouds. But the ROVs captured a near-pristine lake floor, punctuated only by the odd, silent mouths of these deep circular voids. The water around the sites showed no unusual temperature fluctuations or signs of chemical disturbance. The sonar scans conducted over several days showed no new holes appearing and no changes in the existing ones, giving the mystery a frozen quality, like a sudden event had occurred and stopped as abruptly as it had begun. Geological experts speculated a variety of theories, ranging from hydrothermal activity to gas eruptions, though none fit perfectly. Hydrothermal vents are common in oceanic settings and are typically associated with volcanic activity. Lake Michigan, being part of a glacially carved freshwater basin with no active volcanism, does not host the conditions required for such features. Methane vents, which have been discovered in places like the Arctic Ocean, were another contender. But again, these usually involve bubbly plumes and significant chemical disturbances in the water, none of which were present at the site. Seismic activity, which might lead to cracking and subsidence, was ruled out as well. No recent tremors had been recorded in the vicinity, and the formations bore no resemblance to earthquake-related fissures or depressions. Biological processes were also considered. Some marine creatures, particularly in saltwater environments, burrow into the seafloor, creating complex tunnel systems. But the Great Lakes lack such large-scale burrowing organisms. The size and uniformity of the holes far exceeded the capabilities of any known local fauna. Furthermore, there were no biological traces near the openings. No excretions, no shells, no residue. The sterile condition of each hole defied any connection to natural animal behavior. The spatial distribution of the holes added yet another layer to the mystery. Though not uniformly spaced, the arrangement displayed an odd sense of non-randomness, almost like a patterned scatter. It lacked the clustering typical of natural erosion or collapse, and instead hinted at a deliberate positioning. To some scientists, this raised the question of whether the formations could be anthropogenic, caused by human activity. The idea of underwater mining or drilling was floated, but no records, permits, or previous activity in the area supported such a claim. Furthermore, the precision of the holes and the complete lack of residual tool marks or machinery traces made the human explanation feel just as implausible. Beyond the scientific puzzles, the discovery sparked intense public fascination. Though the sites were deep and remote, well beyond recreational diving limits, Their existence ignited curiosity throughout the surrounding communities and the wider scientific world. The idea that one of North America's largest freshwater lakes might be hiding an unknown geological or even extrageological phenomenon captured imaginations. What could have made such holes in the lakebed without leaving any physical trail behind? Environmental scientists turned to sediment core samples taken from the area surrounding the holes. If the formation was recent, they hoped to identify disturbances in the strata or embedded markers. Tiny particles that could tell a story about what happened and when. The results, however, were frustratingly bland. The sediment layers near the holes appeared undisturbed, almost as if the holes had appeared without any impact on the surrounding soil. No chemical anomalies were found, no temperature variations, no isotopic markers of heat or gas. It was as though a cookie cutter had been applied to the lake floor with surgical precision, removing entire plugs of earth without displacing anything else. These findings only deepened the intrigue. More advanced imaging tools were brought in, including magnetometers and ground-penetrating sonar. Perhaps the holes connected to underground cave systems, ancient glacial channels, or even artificial tunnels. The reality was more mundane. The holes simply ended, most of them in conical points, like a funnel abruptly plugged at the base. There was no hint of a deeper structure, no cavern, no pipe, no geological transition. Each hole was a clean incision into the silt and then nothing. One of the more compelling avenues of inquiry considered the possibility of ice formations from the last glacial period, leaving behind voids in the lakebed that had recently collapsed. The Great Lakes were indeed shaped by glacial movement over millennia. However, this explanation quickly hit a wall. If the holes were remnants of ancient ice or collapse features, there would be some signs of aging, smoothing of the edges, collapse, or sediment infill over time. These holes looked new. Not only that, but repeated scans showed no signs of collapse or erosion inside them, suggesting they had not been exposed for long. Whatever caused them had done so recently and quickly. Atmospheric scientists and physicists even weighed in. Could a meteor shower or cosmic event be responsible? Perhaps objects entering the atmosphere had broken apart and impacted the lake's surface with concentrated force. While intriguing, such impacts would leave behind shock signatures, detectable through mineral alterations or shock-melted glass beads. None were found. Additionally, the uniformity of the holes and their limited geographic distribution made a celestial origin unlikely. Meteors don't land in symmetrical, similarly sized formations. As the scope of the investigation grew, the implications of the discovery began to extend beyond simple scientific curiosity. These holes challenged the existing understanding of lacustrine geology and freshwater ecosystems. Their unexplained origin highlighted gaps in both current technology and foundational knowledge. If such features could exist undetected for so long in a lake as well studied as Michigan, what else might lie beneath the surfaces of Earth's other massive inland water bodies? There was also a growing sense of urgency among scientists to learn more, especially regarding whether the phenomenon was ongoing. What if more holes appeared over time? Would that indicate an escalating geological event or a cycle that had simply never been observed before? Monitoring equipment was installed on the lakebed, programmed to detect motion, pressure changes, and any alterations in temperature or composition. So far, they registered only silence, the deep, icy stillness of the lake, with no detectable anomalies. Speculation spread to more speculative corners of science. There were whispers of subterranean currents or unknown hydrological mechanisms, similar to those theorized beneath Antarctica's ice sheets. Some speculated about interactions between Earth's geomagnetic field and regional geology, or even unknown forms of tectonic expression not yet categorized. While such ideas sat on the fringes of mainstream theory, the lack of any definitive explanation made even outlier ideas hard to dismiss entirely. The lack of a clear origin did not stop the scientific community from organizing a multi-phase study. Plans were laid for more extensive sampling, involving deeper core drilling, broader sonar sweeps, and even small submersibles to explore adjacent areas. Interdisciplinary teams, from physicists to biologists to archaeologists, expressed interest. Each hoped that their discipline might hold a missing piece to this puzzle. Yet, even as technology and expertise converged on the site, the mystery of the holes in Lake Michigan remained stubbornly intact. The physical characteristics of the holes themselves also began influencing theoretical modeling. Their neat geometry implied a process governed by consistent forces, yet no known natural mechanism created such structures in freshwater sediments. The possibility of a high-pressure discharge from below was reintroduced, maybe a sudden release of gas or liquid from beneath the lakebed. But again, the lack of residual disruption or heat made this unlikely. If some underground pressure had forced material upward, there would be ejecta, or at least turbulent edges. Instead, the interiors of the holes were eerily smooth. One proposed hypothesis, still under active debate, suggested that the formations could be the result of a rapid vaporization event, perhaps an as-yet unknown interaction between buried organic matter and chemical catalysts introduced from above. In this model, a highly localized chemical reaction could cause sediment to flash into vapor, creating suction pockets. But without evidence of the chemicals or vapor residues, this theory remained only a possibility, albeit a compelling one. Meanwhile, satellite imagery and historical sonar maps were re-examined for any clues. Could these holes have been missed before due to technological limitations? Or had they truly appeared recently? Archival footage from earlier surveys was scrutinized pixel by pixel. While resolution varied, most evidence supported the idea that the holes were new, perhaps forming within the past year. This temporal precision, however, raised as many questions as it answered. What environmental trigger, if any, had set off the process? Why only this part of the lake, and why now? In the absence of answers, the holes became a symbol of the lake's enduring mystery. A reminder that even in well-studied environments, the planet can still surprise. For scientists accustomed to thinking in terms of variables, equations, and systems, the Lake Michigan holes presented a rare and humbling anomaly. They defied classification, refused to fit cleanly into known patterns, and resisted even the most advanced instrumentation. Yet they existed, stark and undeniable, waiting in the silence of the deep for their story to be uncovered. A few weeks after the initial discovery of the mysterious holes in Lake Michigan, the scientific community's attention became more focused and intense. With so many disciplines intrigued, the effort expanded beyond simple exploration into the realm of theoretical modeling and experimental simulation. Laboratories attempted to recreate similar holes using scaled-down sediment tanks filled with silt and freshwater under controlled conditions. Different variables were introduced: sudden water displacement, high-pressure injections, and chemical reactions beneath the sediment. Yet, no model could duplicate the exact characteristics observed in the lake, especially the sharp edges and total absence of debris or crater-like blowout. What made the mystery even more compelling was that the holes did not resemble anything previously seen in other large freshwater bodies. Researchers who had worked extensively on Lake Superior, Huron, Erie, and Ontario confirmed that nothing remotely similar had been discovered in those ecosystems. It was as if Lake Michigan alone had experienced an event or process not mirrored elsewhere. This singularity raised an important question: why this lake and not the others? The physical composition of the lake beds, glacial history, and hydrological cycles across the Great Lakes are relatively comparable. Yet this phenomenon appeared isolated. That discrepancy pointed to a localized influence, something either geologically or chemically unique to the area. Attention soon turned to ancient geophysical features beneath the lake: buried fault lines, possible glacial tunnels, and long eroded bedrock formations that predated the modern lake. While none of these factors provided a direct answer, they did reveal the complexity of the subsurface structure. Beneath the soft sediment layer lies a dense patchwork of dolomite shale and pockets of glacial till. In certain areas, deep fissures run for miles, their shapes mapped only loosely over the decades. Some geologists began to hypothesize that pressurized voids, trapped for centuries within these structures, may have found a release point through the lakebed. But again, without signs of rupture or venting, the theory fell short. The research also began incorporating acoustic analysis. Sound pulses were transmitted through the water and bounced off the lake floor to assess density, structural shifts, and voids beneath the sediment. These surveys yielded some of the most surprising results to date. Directly underneath many of the holes, sonar returned abnormal echoes. In certain places, there was an unexplained soft return, a pattern that suggested hollow space, or a change in material density within the earth beneath the holes. These anomalies weren't visible from the surface, nor were they detected in areas just a few feet away from the formations. That pointed to something beneath, possibly voids or differences in sediment cohesion that could be part of a larger subterranean system. If true, it could mean the holes were just the visible tip of a far more extensive network beneath the lake bed. To probe further, the research team began using seismic imaging, low-frequency waves that could penetrate deeper than sonar and reveal broader subsurface structures. The seismic data painted a strange picture. Beneath several of the holes were long, cylindrical voids extending laterally beneath the sediment. They didn't connect directly with each other in a tunnel-like fashion, but their proximity and similarity in shape hinted at a repeating natural or artificial structure. These tubes weren't carved through the sediment, but seemed more like areas where the material had never settled or had been removed. Their symmetry and alignment challenged the idea that they had formed from glacial action or tectonic movement alone. By this point, the possibility of an unknown natural process became more acceptable, perhaps one never before observed or not yet understood by modern geology. Several fringe hypotheses gained temporary attention, including one involving supercooled water jets escaping from deep pressurized aquifers. The theory suggested that underground fresh water trapped under high pressure could, under the right circumstances, break through the lakebed with such force that it evacuated entire columns of sediment vertically. But to do so, with no residual turbulence, no sediment fan, and no heat transfer was again difficult to justify. Still, researchers didn't dismiss it entirely and began studying fluid pressure maps beneath the surrounding terrain to look for aquifers, water tables, or shifting subsurface conditions. Another angle came from geomicrobiology. While the holes seemed too perfect to be biological in origin, microbial activity can alter sediment cohesion and structure. Certain bacteria and archaea can metabolize iron, methane, or sulfur in ways that destabilize surrounding materials. Could it be that microbial colonies deep within the sediment layers had created pockets or voids, weakening structural integrity until collapse occurred? Teams collected sediment samples from within and around the holes and analyzed them for microbial DNA, gas composition, and chemical gradients. Results revealed some elevated microbial activity, not unprecedented, but more than in control samples from nearby undisturbed areas. While this offered intriguing insights, the microbial hypothesis still couldn't account for the sharp geometry or sudden formation of the holes. It was, however, one of the few explanations that didn't require exotic or speculative mechanisms. Meanwhile, back on the surface, the quiet enigma of the lakebed began shaping environmental discussions. If these holes represented an ongoing process, even if natural, what implications might they have for lake stability? Could they lead to larger collapses, affect aquatic ecosystems, or destabilize nearby infrastructure? Researchers began modeling potential sediment collapses under various scenarios, especially near shipping lanes or underwater pipelines. One simulation revealed that if the holes grew in diameter or multiplied at a consistent rate, large-scale slumping of the lakebed could occur over decades. This would not pose an immediate risk, but it raised questions about long-term sediment displacement and water quality impacts. Biologists, too, entered the conversation. Lake Michigan is home to a diverse array of freshwater species: fish, mollusks, crustaceans, many of which rely on stable lakebed environments for breeding or feeding. While the hole sites were mostly in deep water zones, not traditionally active with benthic life, the presence of unusual formations could disrupt sediment chemistry, water currents, and even acoustic navigation among aquatic species. Studies began on whether the holes acted like acoustic chambers or created microcurrents that might affect fish behavior. Although early data showed no significant disruptions, sensors placed near the formations occasionally picked up irregular low-frequency vibrations, faint pulses that did not match known geological or human-made patterns. Curiosity about the broader geological context prompted teams to begin comparing the Lake Michigan holes with strange underwater phenomena found in other parts of the world. While nothing exactly matched, there were loose similarities with structures found in the Black Sea and the Baltic, where unusual seafloor pits have occasionally formed due to gas seepage and sediment liquefaction. These pits, however, are usually conical, irregular, and transient, often closing up after a short time or changing shape. In contrast, the Lake Michigan holes remained stable, silent, and sharply defined, but the comparisons were helpful. They introduced researchers to methodologies for monitoring ephemeral lakebed changes, including the use of underwater time-lapse imaging and sediment displacement tracking over long durations. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on these holes? What do you expect will happen? We want to hear from you. Thank you for watching and see you next time.